know, you got like words for it's like, how can I make this like 2 words?
So I'm pretty sure you
give me like a whole sentence to describe this word in your sentence, describing it.
Did they redo your room? They like totally moved it in your space.
Really hard test. Just to make translation and capture everything without it being like huge or really complicated to read.
Hey, anybody got an exam for me?
I do. It's not staple, but I numbered it.
Do we have a stapler in the room? Somebody's gonna have one. Yeah. Yours is what?
Yeah, mine's done. I just have to like go back through it and make sure.
Thanks. Yeah, do what you need to do. And you're totally ready. You feel okay about it. Okay. Cool. Thanks.
Make sure everything's right.
Anybody else got one for me?
Dot, every last.
Anybody need a Dropbox to plunk one into? You would like that? I'll make a Dropbox. Okay.
Eventually, I might want that.
I was just gonna write it. Yeah, let me just like put it all into a stock.
Well, yeah, you just
Just screenshots. Yeah, I was just saying like type it up.
type all the code.
Easy. Really fun. It's like such a pain.
What's that?
If we wrote it down and just like manually type it into Word, it's easier.
Brutal.
No. It's harder to keep going.
Yeah, I'd use LaTeX. That would be a lot easier once you know it. All right, my friends. Hello. Yes, I know we're all excited to have the return of our dear friend Lamina. So if you could get me your exams in the next day, today or tomorrow, that would be ideal. I'll open up a Dropbox and you can digitally submit. Anything on your minds? Yeah.
Let's say I have a question about that exam. When would be a good time to ask you that question?
Probably any time in the last week or so, but yeah, I have office hours after class.
Okay. It's a small question, so I'll just
It's
ask
all
it.
good, it's all good. We'll probably have a few minutes at the end. That's okay. Thank you for taking my harassment. Any other question? Not after that exchange. All right, so we are gonna start talking about differentiation. And I have a question I'm gonna pose you. Exclamation point, because things are gonna start, everything's gonna build. What you're gonna see is a really cool stack of ideas that we've been building. One uses ideas from the other, or can. But for a little while, we're gonna take a very cool excursion into Taylor series. And, they're amazing.
Taylor series.
They're one of the greatest things. You're gonna love them now. You're gonna end up loving them. But before we get there, let me ask you a question. So I've got some data. X, Y, let's see. So, I should have written down some, but I'll just make some bullshit up. Because that's how I roll. 1, and then 3. Let me actually make them evenly spaced on the X. And then, how about 5 to make things spicy? We got a data set. Always look at your data. No matter what you are doing, look at your data and just see what you can see. Use various tools. Right now I'm using the most primitive of tools. Writing on a freaking board. And I think that's a 5. So I've got those data points. So my question to you all is, how could we, because I want to see what you come up with, tabula rasa. That's like some Latin shit, right?
Oh.
You don't know?
No.
Tabula rasa? What is that phrase? Is that Latin? Somebody Google it.
Can you spell that?
This is... It means blank slate. You're like, "Nah, not in Latin." Maybe it's not Latin.
Oh, it's a Latin phrase.
I thought so. Tabula rasa, this means blank slate. We're starting with nothing. So how could we estimate, if these functions are a sample of pairs from another function, some true function, f of x, how could we estimate f prime of 1 here? Just take a minute, think about it, come up with some idea, and you can use things that we've talked about, or you can use something completely different. We're going to actually talk about multiple ways to do it today. So think of these, maybe it's distance versus time, you know, and we want to estimate the velocity at time t, so maybe we're looking at the velocity at time 1 second, same thing. It certainly looks weird, right, because of just the way the graphs go down and then up, or the dots go down and up. Anybody got anything thinking about, just top of the head? You know, no wrong answers. Josephine.
I'm like kind of suspicious that it might be 0 because wouldn't it turn if you connect all the dots? 'Cause like,
Oh, cool. Yeah. So you're like you're drawing this in your head,
yeah.
and you're thinking of a local min. Yeah, that definitely could be it. But how would we know that it isn't right like that? So it could potentially have some negative slope. So I like the way you're thinking. Definitely. And the idea of putting a graph on top of these dots, that's a great vein of thought. That's a very fruitful vein of thought. And that's kind of a hint as to maybe what we could do just using some of the more precise tools we have. Yeah.
Could you do make the 2 splines thing again and then like use like one equation and like differentiate it?
Yeah, so we could fit some curves to these, right, in a variety of ways. So Josephine's idea was fit a spline here. Now the only trouble with the spline is we'll need to assume, so we're going to fit maybe some cubic here, and then some cubic here, something like that. That's a weird cubic, but fit 2 cubics in here, and then go to the knot and grab that slope information. Remember how we actually use that slope information here? We want those 2 to be the same tangentially there. So we could grab the knot slope. And that would be a cool idea. That's a very good idea. Any other ideas? Maybe something with lower degree. These are 2 cubics. The computer's going to do all the work for us, so we don't care. We'll make the computer suffer and, you know, do everything. Don't worry about computational struggles. What else could we do? Does this look like a good plan? Do a linear fit like that? Now, why is that even?
Because you can't take a derivative of a linear fit.
Definitely, I don't want this. There ain't no derivative at a corner, right? What's the tangent slope? Pick your favorite. What else what's one of the earlier things? What did we do before splines? Polynomials. What kind of polynomial could I fit here? Second degree polynomial. So I could fit a parabola and use that as well. And that's kind of what you were doing, Josephine, right at the beginning. You were fitting a parabola to this, but your parabola, min dot there, and that's what I was just saying, we would want to actually do a full fit and figure out what that equation was. So one way, let's write out some things here, is use spline approximations. 2, we could use just the Lagrange interpolation scheme. We could also use Newton interpolation And I'm just gonna put that in the same. Does that all make sense? Yeah, I mean, so we could just literally go through it. Let's just do it real quick. Let me just do a divided differences table. So 0, 1, 2, 2, 1, 5, because I'm actually kind of curious how this is going to compare to some other things we're about to do. So first divided difference here is going to be 2 minus 1 over 1 minus 0. That's 1. The next one's going to be 5 minus 1 over 2 minus 1, so that's 4. Next divided difference is 4 minus 1 over 2 minus 0, so 3 halves. So that was so quick, right? Oh, did I do something wrong, Blue?
I just want to make sure.
Yeah,
For
yeah.
the first one, would it be 1 minus 2 or?
Thank you.
You did
I
like
did.
different
You're
orders
right.
in
You're
both of
so
them?
right.
So
I-
I just, yeah,
Good call. Good call. I did different directions, didn't I?
yeah.
Yeah. Thank you for that. So this should actually be -1 here. Thank you. Good catch. So then this would be 4 minus -1 over 2 minus 0. Cool. Thank you. So then I've got my interpolator being 2 plus x minus 2 plus 1 times x minus 0 plus 5 halves times x minus 0 times x minus 1. Let's actually crank it out a little bit more. So this is 2 plus x. Oh, that's so pretty. This is easy enough. 5 halves x squared minus 5 halves x. And then we simplify. So we're going to get y
It
equals.
should be negative x.
Right after the 2.
Thank you.
You no on the first.
Yep.
Yeah, you dropped it. Right, because it's 2 plus negative 1.
2 plus.
Negative 1 times x minus 0.
What did I have here?
So it should be negative. Right, because it was negative 1 in the top.
Oh, thanks, because I didn't propagate that down. Thank you, sir. Yeah. Okay, awesome. Good stuff. Thanks, Liz.
No, you're good.
That's good. So how's this? Is everything else looking okay? I think so. So 2 minus 7 halves x plus 5 halves x squared. Cool. And we could graph that and figure out where, we could like use methods to figure out the vertex. In fact, we're going to use a calc 1 method. So if I find y prime, that's going to be negative 7 halves plus 5x. The vertex would be where this equals 0, where I have a horizontal slope. So let's see where that vertex that our friend Josephine was visualizing would be. So I guess 7/10 would do it. So at 7/10, so it was actually, we're not where I thought either. It's actually a little bit right there, 7/10. That's the minimum. And so then we have a very steep parabola. So that's cool. So we can get at that this way, but that's not actually what we wanted it for. We were curious, what is the slope at 1? So y prime evaluated at x equals 1 is going to be negative 7 halves plus 5, and that is 3 halves. So I've got an estimate, 1.5 is the slope estimate for this point right here. So m is approximately 1.5. Let me stop for a second. Let me let you catch up. I know when I start doing calculus, maybe I get a little out of control speed-wise. So I'd prefer that. So let me know. Also sloppy-wise, as that's why Lou's here. Lou's my manager. Does this all sound reasonable for a plan? Well, we're going to look at some other methods today. So this is a completely legit way to proceed. Let's just record that 3 halves, and this, if someone could just make sure that this data and that slope estimate is recorded, because I want to compare it to what's about to happen. All right, so if there's no questions on that, let's do a quick review of some Taylor's. Well, actually, let's talk about the problem in taking a derivative, and this will lead us in. Why are derivatives challenging for a computer? Can you tell me some reasons? What do you think? Why are derivatives challenging for a computer? What's the definition of a derivative? Let's maybe start there. We know f prime of x is what? Any version. Anyone except Josephine. Yes, Ava.
It's just like how the function changes over x usually.
Yeah, yes. It's a rate of change, absolutely. So we've got f of x here, we've got x right here, and it's an estimate of that change. Can we be more precise? That is so true. That's all good, very heuristic. Let's get mathy. Luke, I see your fingers unfurling.
I'm thinking about the limit definition where it's like limit as h goes to 0 of like f of x minus h times
I'm gonna do
or plus f of x over x plus h.
cool. So I kind of just
Yeah.
tweaked that.
No,
tweaked
I
that a
just-
little.
it's been a while. I just had to
I was
watch
editing
this
as it
one,
came
yeah.
through, but yeah, that's the one I'm thinking about. Yeah. So we take x, where we want the derivative, we move over some arbitrary distance at h. So this is where the x plus h is. Here's h. Here, in this picture, it looks like h is positive. It doesn't have to be. H could be negative, and x plus h would be to the left. And that's okay. Because this limit, just to talk about this limit is a two-sided thing. Why, when you say a limit exists, you're saying from the left and from the right, I get the same result. So if I do this from the right and I do this from the left, it has to be, those answers have to coalesce. That's all about the tangent lines coalescing. So this has two limits in it that need to exist. But when I come back here and I've got this, think about what this quantity is. On top I've got the vertical change. So there's f of x plus h minus f of x, just the change in height. And then the bottom is the change in input. So here we have change in output over change in input. And this is what Eva was saying. I'm trying to review derivatives because it's maybe been a while and I just want to make sure we have all the different ways of thinking about these beautiful beasts. So then, right now, if I just do this for a fixed h, I get an approximate tangent slope. I get the secant slope. So a secant is when you have two distinct points and you find the line between them. Right now, we've got that. As we let these two shrink together, either this way or this way, when h is negative, when h is positive, we get this point moving down toward this one and hopefully get that tangent slope if the limit exists. What is the problem with this in a computer? What is the problem with this? Could be infinite, yeah, we could have a problem with the division for sure. Is that what you're thinking, because we're dividing?
Maybe.
That's cool. Josephine?
Sorry.
That's definitely true.
Since like the limit goes like infinitely close to 0, like you have to tell how precise you have to do the computer, like or how many repetitions to do it for.
Yeah, exactly. We've got the machine epsilon, right? Remember what the machine epsilon is the smallest thing that the machine can distinguish. It's like a quark. It's the system quark. I don't know, there's probably sub-quarks, I should shut up about that. But it's an essential smallest unit. It's like the Planck constant, right? Does that make sense to my physics friends? Planck constant, the smallest thing we can measure in the universe? You know what I'm talking about. So something like that. So none of those analogies made the slightest bit of sense. It is the smallest Lego in our Lego set. So, so the machine epsilon, where was that? It was like 2 to the negative 16th, I think, for a, or was it 32 for a double precision machine? Is that, or was it, no, it was something a little weirder, right? It was like 2 to the negative, yeah, it was something because the IEEE doesn't let us use everything. Does anybody have that written down? Really good. Was it 17? It might be.
Sounds familiar.
It sounds really familiar. 53, that's it.
I've written down 52.
52 also. 52 is also a great number. There we go. So 2 to the negative 52. That's the tiniest thing that a double precision machine like we're using can distinguish. So this is equal to the machine epsilon equals smallest observable. That's sounding very physicsy. I don't give a shit. Smallest observable number. So I can't keep going. As Josephine said, a limit says, you tell me how close you want to get, and I'll tell you, you can get that close and closer. So limits are all about a game of call and response. Get this close, I'll definitely do it. Oh yeah, we'll get this close. Absolutely, I can do that too. So this is as close as the H can get to 0. This is, in some ways, our 0. Yay. We love 0, but that's as good as we can get. So we can't take limits. Long story short, no limits. We can't take true limits in a computer because that requires continuity. Limits, let me put a couple of more things up here, require continuity. Computers are discrete things. So we're going to have to deal with that. So given that, and I can't take a limit as I go to 0, what could we do here? What's another option? And let me actually make this a little trickier for you. We've got a data set, and we can't really make up new data. We don't want to make up new data. So let's say I have a data set, and it has step size 0.1 on the input. So this is my input, and then I have output values over here. They can be whatever you want them to be. But here I've got the input. These are my x coordinates. These are my y coordinates. How could I estimate the derivative at 0.1? Well, we'll go ahead and put some numbers in there so we have them to anchor us. How could I estimate without going to a fancy formula? How could I get a rough estimate of f prime at 0.1? Without going to Lagrange interpolation, no splining, just let the machine freaking do it. Using subtraction, division, addition, and multiplication. What can we do here?
I mean,
Oh, yes, ma'am. She was pointing to you, so that was why I was laughing. You didn't see that part.
if we were in a physics class, we just take change in output over change in input, and then we'd say that's a derivative.
That sounds like something a physicist would do.
Yep.
It's not a bad thing to do. So what you're saying to me is I could say, can you give me some differences here, Eva? So I want the derivative here.
So like 2 minus 3 over 0.1 minus 0, or if we're doing the full thing, like 7 minus 3 over 0.3.
Oh, so you're really going way out here.
Yeah, I mean, depending what we want.
What is that you're saying, Daniel?
Wouldn't it be less precise if we did it that big?
It would definitely be less precise. Let's draw a picture so we can see. So the closer we can stay to the point, the better it's going to be. Because this information, like you were saying, the information further away is going to relate less to the slope. There could be a quick change. 0.3, and so what do we got here? 3, I include this, boy, is that kind of an outlier compared to the other three. Looks scary to include this 0.7 as our estimate here. So if I did that slope there looks mucho different than this slope here or this one here. So we're gonna try to stay close as possible, but you have the right idea. So what we could do is we could say this is approximately, and we're gonna let h be, this h, the smallest we can let it be in this data set is 0.1. That's the smallest change we can observe in this data set. So we're going to use this and hope it's small enough. It might not be, but what I would get is this is going to be f at 0.1 plus 0.1. So I move over just this one unit here. So in other words, this is f of 0.2 minus f at 0.1. So I'm looking at the change between these two values here, this value and this value. What is the drop or rise? Here it's a drop. Over the total distance I moved, and that's 0.1. So this is my x, this is my h, and that is my x. And this is my x right here, just thinking of this formula. So let's see, what do we get? We are going to get f at 0.2 is 1, minus f at 0.1 is 2 over 0.1. And we get negative 10. Is that right? That's insane. But the scale here is really weird, so it's much steeper than it looks in terms of that, right? This is 3, and that 3 is the same as 1.15 here. So negative 10 is our estimate there. This is a completely legit thing to do. Did you have a question about it, Daniel?
No, I say it seems right, just because of how small the scale is on the x input.
Yeah, absolutely. Yeah, agreed. So this is our first method, but I want to get at it a different way. Let me just, let me summarize. If we use f prime of x is approximately f of x plus h minus f of x over h for small h, small magnitude h. This is reasonable. What we're going to learn over the next week and going into next week is how to make this so accurate with just simple, no interpolation, with just simple math. We're going to make this so accurate you aren't going to freaking believe it. We're going to develop our own formulas. I'm going to show you how these formulas are developed to approximate derivatives. First derivative, we'll start with that. Maybe today we'll end with the second derivative. We've got a challenge for you. And it all comes down to understanding Taylor series. So, Eva, you're going to like them after this. You're not going to feel bad about them. Let's recall Taylor series. So suppose I have a function f of x, and it is differentiable till the cows come home. And that's just the Midwestern boy way of saying I can keep on differentiating with no problems. So, and if f is infinitely differentiable, that's the smoothest you can get, differentiable, on some interval about x. Now that interval might be all the real line. It might be just a little interval from 0 to 1. We don't know. It depends on the f. But we're going to assume that we can take derivatives. So put a little here, put a little note. We can take derivatives of every level. Cool. So, Taylor series, Taylor's theorem says this. If this is the case, he's probably got some fancier math conditions than I'm putting up here, but we got the heart of it. Taylor's theorem says I can write f at x equal to, let's put a little sub-zero right here. because that x might not be the same as that x. This is a general one. So f of x equals the function at that point, x naught. This is called the center of the series. It's where we're expanding around. Plus, see, let me give you a second. What do you remember of this? Write down. Just force your brain to dig in the cellar, go through the boxes. How does this go? To see what you can remember. Take a minute. And it might not be much, and that's totally cool. It's all private, right? It's all very private. Except I'm gonna come watch you. Oh my God, if I'm gonna miss you, like, what am I gonna do when you graduate? Oh my God.
Don't make me cry. I'm like,
Okay,
this
right.
close to mental break.
Okay, no.
No mental graduation will be that.
Let's not think of it. You're gonna be here forever.
Yes.
Yeah.
You'll be here forever. All good. Great. If you want, I will ensure you do not graduate.
We don't need to go that far.
You all saw her hit me, right? She just hit me. It's on camera. I will be filing charges. My friend. All right, let's not linger too long. Somebody help me out. I got you started. What's next?
Can we just guess?
Oh, yeah, please, yeah.
I feel like it's something like f prime, like x not minus, or something over like 1 factorial.
Oh, that's
and then
so
like
good.
plus and then f.
I'm gonna put this part in there.
Oh shoot.
Do you remember that? So now I bet you can get the next one now, because that was great. What's the next
Then
one?
the next one's like f double prime x naught
Yeah.
over 2 factorial next to. Oh. It's x minus x. Oh my gosh. D squared after that.
Yeah, like that?
Yeah.
Yeah. And so on. So the next one would be f triple at the center over 3 factorial x minus x naught cubed. And then continuing on, and this is kind of the part, I hate this table. I don't hate you, table, but you really are not helpful, table. Okay. Wow. The rest of it, I'm just going batshit, I don't care. Hulking out. I'm super punchy today. I don't know if it's from the flu and COVID shots at the same time, but I feel hulking. And then
There's steroids in this.
That's a big cup of steroids in the morning. And then at the general term is the nth derivative at x naught over n factorial x minus x naught to the n. And that keeps on rolling, and that never has to end. This is one of the most important things you can remember. So like, this is a good, I'm so glad we're talking about this, because this is probably one of the most useful facts to know about math. Because what it does is it takes any function you want, including the transcendental functions, like sine, cosine, e, natural log, arctan, all the weird functions you could come up with, and turns them into a polynomial. It turns it into powers of x. This is all stuff a computer can do so well. Computers are great at multiplying, adding and subtracting, and dividing as long as we're safe. We have to be careful. Division can get a little weird. If you divide by too small a number, you're going to you're going to see a lot of error pop up. If this number gets too big, things are going to get truncated. You're going to lose detail. So if you divided by, for example, a number like that, probably going to be some error that pops up. Because the thing on, depending on what's on top, that's going to be a big ass number. Detail will get lost. But the computer can do all this stuff, and these are cool numbers. These are just lovely whole numbers, 2, 6, and factorial down the way. So that's going to be our friend for the next couple days, just this formula. And I want to rewrite it in a way you've probably never seen it written. But it's the way most mathematicians and probably physicists would actually use this formula. We're going to replace, I'm going to let x minus x naught be replaced by h, because h is just the difference. H is the step away from the center x naught. And remember how we would use this. We would say, I'm curious as to the value of f of x near x naught, and I would plug that in here, and then I would just work through as far as I wanted to get a better and better approximation. So let's rewrite this formula. That means that x naught is now, so x naught is x plus 8. Is that, that's x naught is x minus h, isn't it? I want this to be x naught plus h here, so hold on a second. So let's see, I want x to be replaced with x naught plus h, because I want that right here. So that means we're going to replace.
That's fine, because then it's x minus x naught, and that's what's in your equation anyway, right?
Yeah, that's what I was shooting for. Okay, cool, that works. Okay, thank you. Yeah, good. I know what I want. I just made a bad step. Oh, yeah, this all makes sense. Was it right before, and I was just being fried?
I think you were trying to get it for x naught equal to x plus h instead of x.
That was it. Thank you. Yeah. So it was okay. Cool. So this formula is going to become f at x naught plus h. So in other words, our center plus a perturbation. This is known, this x naught. The h is the step size. Equals f at x naught. So I'm just copying this formula down. But notice that each of these guys becomes an h. So this becomes h squared, this becomes h cubed. Much more elegant way to write this formula. So it's going to become f prime at x naught over 1 factorial h plus f double prime at x naught over 2 factorial h squared, blah, blah, blah. Much nicer. So you just, if you know this, and you know this, you can get estimates for these other things. So in other words, let's rewrite it. First off, call this star, because we're going to come back to it many times. So formula 1, take star and subtract f of x naught from each side. And I'm going to kind of walk through this slowly because this is what you're going to need to do. So subtract f of x naught from each side. And what we get then is f at x naught plus h minus f at x naught equals, we're not going to write that 1 factorial anymore. Over 2 factorial f double prime h squared. Cool, you see the derivative almost there. If I literally solve for f prime at x naught, I have to divide both sides by h, and look what happens. So then, divide by h, which we're going to assume is non-zero. There's some really cool stuff. This week, I think you're going to find some of the most mind-blowing things, especially on Wednesday. So divide by h, and what I get is this. That is the derivative definition. Equals f prime at x naught with no times h, because we just divided it away. And then there's this stuff. And I want to talk about this stuff for a minute, but I want to note that I want to write a couple of terms out here. That's triple prime x naught h cubed plus blah, blah, blah. What I want you to notice, is that looking okay? Just so. Oh, didn't take out, thanks.
Double
I tell you,
H.
yep, thanks, thank you.
No, you're good.
Now I'm good. It wasn't good without your management. Is everything okay still? Okay, cool. Getting a little scared there. Got my boss in class today. So this stuff here, notice how you can factor an h out of all these terms. Does everybody see that? That there's at least an h in each one of them. H squared, h cubed. So I can actually factor an h out. And what I'm going to get is h times a constant, whatever this quantity is right here, plus something h cubed. So let's just go constant. How about constant 1, constant 2, h plus on down the line. The key thing is all this stuff is divisible by h. So what I'm going to write is the following. I'm going to, in my mind, move all the stuff after the plus sign to this side. So it's going to be subtracted. So what I'll actually have is f prime at x naught equals, and I'm going to have this here over h. And then I'm just going to have all this stuff. I don't know if it's positive or negative. All I know is that it has an h that I can factor out. So I'm going to write a big O of h. So this is the remainder is approximately h times some constant. Roughly. And the constant I'm thinking about is that first one there. And then the rest we're going to not think about a lot because h is going to be a small number. And so the other stuff is less important in that series as we go down. And let's put one last thing here, when h is small. That's the really important thing. So have you seen this big O notation before? CS people must surely have. Physics people?
Not in class here.
Not in class here?
At an internship.
Oh, really?
Yeah.
Oh, we're getting fancy then. La-ti-da. All right, so this notation, this is called big O notation. And it's a way to express essentially what I'm trying to say here. Let me show you another example. If I say a function g is big O of, let's see, if I say g of x plus h is big O power n, then what this means is that g of x plus h equals h to the n. I can factor an h to the n out of this stuff, and I'll have a constant 1 plus a constant, and these aren't the same constants as I have over there, like so. But essentially it means that there's just an m here. We can put an approximate like that. So you can factor a power of h out. So if I said something was big O of h cubed, then that would mean I could write it as h cubed times some other stuff. I could factor an h cubed out. So that might be a good way to think of it. This means we can factor an h to the n out of the expression for g of x plus h. Thomas, is that a question or just no?
No.
Cool. Okay, that's all good. You don't take it down. Don't take it down. That's all good. So let me rewrite what just happened here. I took this expression, solved it for f prime, and what we got was f prime of x is equal to f of x plus h minus f of x, and now I'm just removing the not here, over h plus big O of h. This is how I estimate my error. Estimates the error in the approximation. This probably won't be true. This won't be the whole derivative. How far away is this from the truth? This much right here. Let me stop. Make sure you see that. The key thing is that big O represents our error. All right. This is called, so this rule right here is called a forward difference approximation for f prime of x. It literally says, just go over your next step. Here's x. Here's x plus h. It says, just do this natural thing that several of you were talking us through. Find that slope right there. Here's your change in y over your, change in f over your change in x. What is that? It's the best we can do. It's as tiny as this can get down here. So it's really a secant line approximation. But if we make it, if we want it to be a tangent line approximation, it can, and this is how far off it will be from the truth. Let's do this a different way, because I want you to see right off the bat a better way to do it. And I bet you've never taken a derivative like this, but it actually kind of harkens back to what you were seeing, Eva, at the very beginning, where we went a little further out. So this is really cool. Now let's get a different formula. And that's kind of what this week is about. So first off, I'm going to write up my original. I'm not even going to put the sub-zero in there anymore. By the time this week is over, you should be able to pretty accurately whip out these Taylor series in general. And I'm going to go out to the third term, third power of h, and then here, what could I write? Big O of what? What's the big O for the remainder here in the Taylor series? What's the next power of h?
H to the fourth.
Mm-hmm. And everything else will have h to the fourth or higher, right? So all this stuff out here will have an h to the fourth at least in it. Next one's h to the fifth, h to the sixth. But either way, I can factor an h to the fourth out. So I'm just going to kind of write that like that as a shorthand for yada yada, but we don't want to throw away the yada, you know? All right, let's check out this. F of x minus h equals, could you crank that series out using this one, please? I give you a second. What the hell am I asking? How could you take that first formula and get the formula I'm asking for? Like we're like on the cusp of magic. It's incredible. Oh, you're fine. You're fine. I don't even want to go back there. Thomas, you got this one. You think you do? I think that's the you think you do. No?
No, that's the I'm confused phase.
You're confused? Okay, cool. We'll get you straightened out real soon. Is anybody not feeling confused and maybe has a sense of what, as Josephine said, take a guess? Do you have a guess? Yes, ma'am.
I'm a little suspicious suspicious because I know h could be 0. Because, I mean, negative, sorry. I may be stupid.
No, you're not. No, you are not being stupid.
Because I know you're saying like it could be in front or behind the x. I don't know if like adding or subtracting it is.
I see the confusion, and this is probably what Thomas is up against. So let me write up a better form of the Taylor series that I think is going to make your life way less painful in the next week. So this Taylor series, this Taylor formula could be written like this. I'm going to put a big old, I love doing this. People like my boxes and triangles for function input. So x plus something is equal to f at x plus f prime at x times that something. This is h, but it could be sine of h, could be anything. I could put anything I want in there. I could put Kyle in there and just copy it across. And then this is 1 over 2 factorial, f double prime of x, whatever's in there squared, etc. Does that help? What's in the box? Negative h. Yeah. So if I put negative h in here, it goes here, it goes here, and now I've got enough to maybe sort the rhythm out. Does this make sense? I'm going to pull that negative out in front. So this first term doesn't even get touched by h, but the next one sure does. Right? Instead of h, I have negative h. I'm just going to pull it out in front. What happens to the next term? Same, right? It doesn't get changed because it's h squared. So this is plus 1/2 f double prime of x h squared. What about the next term?
You're subtracting the same term?
Yeah, this is h cubed, so it becomes negative h cubed. Because cubing's odd. Okay, it looks like I'm getting a lot of head nods. This is much better feeling. And since this doesn't care about sign, S-I-G-N, it's still kind of the same. There's going to be negatives and positives there, or negatives that weren't in the original. Who cares? We're not thinking out that far. We're bringing our focus right here. I'm going to take these two expressions and I'm going to subtract them. Because think what I want to do. I'm looking for a formula for f prime. So if I add these, that's not going to help. Because if I add these two formulas, these will cancel, and I won't have f prime in the expression at all. So I'm going to subtract so that I preserve this. Do you see anything cool that might happen when I subtract these two?
The odd ones go away?
Or the even ones go away, yeah. Or every other one goes away, maybe that's what you're thinking. So f minus f cancel? Is that what you were thinking? Okay. These don't cancel. What do I actually get? So 0, right? What happens here? What's the next term? That
2 times f prime of x.
2 prime, f prime of x h, dead. Other stuff will die back here. And then what I'm left with is just 2 of those dudes. So 2 over 3 factorial f triple prime of x h cubed plus order h to the 4th stuff. Do you think that order h to the 4th stuff, I could make a better claim about it? So I put h to the 4th. Is there actually an h to the 4th in this expression? What's the next term? The 5th, right? The h to the 5th is going to be the next term. So this is actually that. I don't need to put the 4th in. Let's get as much, sorry Tracy, as much detail in here as I can. Let me know if you understand that or not. Let me know if you don't understand that. I'm happy to explain it. I'll add a little bit of more terms to the board. All right, so this minus this is that, and I want this. So I'm going to solve for it. So solve for f prime of x, and what we get is f prime of x. I'm going to move it over to this side, and then I move all this shit to, essentially to the other side. So f prime of x is going to be 1 over 2h, because I will divide by it. But first I'm going to subtract stuff. So I would have subtracted off 2 over 3 factorial f triple prime h cubed plus, and then I'll put minus here. We don't keep track with order notation, but it might make you feel better for today if I say that, just so you can see the moves. So what I did again is I subtracted both of these from this side, divided by 2h, and then flipped the equation. Let me stop. Wait, did I lose some?
Well,
I feel like I lost some.
you're missing the f of
Yeah,
x plus h minus f of
yeah, thank you.
right?
Thanks,
He's
yeah,
still in there
yeah,
somewhere.
absolutely, yeah. So when I got that, yeah, thank you. Son of a gun, now I got myself too excited. You're right. So, let me slow down. I'll just keep this shit here so that I don't confuse myself. So I'm gonna have 2h f prime of x equals, move all this stuff to that side. Yeah, that's what happened. So these are still here. Minus that, minus the order h to the 5th stuff. There we go, much better. Now divide both sides by 2h. And we're going to get our estimate. And I claim that this estimate is in order of magnitude better. Just by doing the formula differently, we're going to get twice the number of precision points in our estimate. So let's simplify a little bit more. What this really says is that f prime of x is equal to, canceling the two h's, 1 over 2h f of x plus h minus f of x. And I'm going to pull that piece out separate. And then when I divide this term by h, what does it become? What order is that computation in terms of h? How many h's are left? 2. So I'll have an h squared. And that'll be the lowest power of h that I see. What will this guy become? Order 4, right? So it'll be h to the 4th. I'm not worried about the 2, I'm worried about how the h's cancel. So here I would end up with an order h squared error. Check that out, make sure that seems legit. So if h is small, if h is a small number, Lou, is that a question? Yeah.
How did you take f of x minus h into f of x? Sorry, I think I just missed that.
You didn't miss it, I copied wrong.
Oh, okay.
Thank you, sir. Yeah. Thank you. Thank you. Looks like I'm not going to get paid this week. So, this is a very different thing than we've seen so far. So if this is x, and here's x plus h, and here's x minus h, this thing actually grabs f here, and subtracts. So this is going to be the difference. Notice that it doesn't even involve the center. And then it computes the slope of this line. And how far is this distance right here? 2h. So this is just the derivative estimate taken at these 2 points instead of these 2 points. This is called a central difference. Now the forward one was when I used just these. I went forward and found the estimate that way. This one is a central difference estimate. And it's really important that we know these because we're going to exploit these errors to, oh my God, something so crazy. Like I keep saying it, but it really is amazing. Central difference approximation. So let's actually see how this would work. Let's make this work. Let's look at something we can verify and see what happens. So we're going to take e to the x because we know about that pretty well. I heard, Kyle, I heard your sister woke up from anesthesia And there's one of the first things she said was the integral of e to the x is e to the x.
What a nerd. She actually said
Your mom told me this morning. I think it's amazing. I think it's great. It should be a new awareness test, like a roadside stop thing. Like, give me a calculus fact? Yeah. Kyle's sister was an awesome math major, but she did not like math. That's true, isn't it?
It's accurate,
She liked fiction writing, and that's what she's doing. So it's crazy that that's stuck in her brain. Absolutely insane. Okay, well, yeah, so we're going to take e to the x, and what we want to do is approximate the derivative here. So find d dx of e to the x at x equals 0. What is the answer? 1. Yeah. Because as a barely conscious human told us, who hasn't looked in math in 5 years, the derivative of e to the x is e to the x. I'm just saying it in different words. So we know that we know that the derivative, I'm just gonna, just in case you don't remember, so the slope at x equals 0 is e to the 0, which is 1. Cool. So we know the truth. Let's use our techniques to estimate it. So we're gonna make a table. We're going to let x be negative 0.1. So here I'm going to use h is 0.1. This is my step size between my samples. 0 and then 0.1. I'm setting this up because I want to work at 0. I want to be able to do the forward difference, and I also want to be able to do the central difference, which is the neighboring points of where we want the derivative. So could someone help me out here? I do need a calculator, friend. Could someone give me an approximation of e to the negative 0.1? I mean, I can do it. See if you can do it before me.
Which one?
Any of them.
E to the negative 0.1
Yeah.
is it's 0.9048. I don't know how far you want to go.
That's
Okay.
one. Give me 2 more, please.
2 more. 3.7.
Okay. Cool. And then I got this one.
Yeah. And then the next one's 1.10517.
Cool. Let's go one more.
It'll be 1.
Okay. Thank you. So here's our data. We don't know this function is e because we just got this data from someone. And they asked us to estimate the derivative at 0. So this is f of x, this is x. If x is our center, or the point of interest, then f prime at 0 using the forward difference. So I put FD there for the forward difference. Let's write it out. So this is 0 plus h, 0. I'm not filling in what I know h to be yet, just so that you're not getting totally lost by what's happening here. And then there's some error here. And now I'm going to crank this through. So this is actually, let's see, we're going to use h equals 0.1. So this is f at 0.1 minus f at 0 over 0.1. So Lou, would you please take the 1 minus the 0.9?
Oh.
Or yeah, 1 minus, so this minus this. Oh, no, sorry, this minus this. I'm going backwards. This difference in those. I guess I can do it, can't I?
Yeah.
Yeah, I think I can do it. Thanks anyway.
No, you did.
Over 0.1. Yeah, I think I got it. And I can do this too. Look at me. Being able to divide. That's just multiplying by 10, so 1.05171. That's our approximation. Kind of 1. Not great, but kind of one. Let's see what our central difference is going to do for us. So the central difference says, so CD is going to be f prime at 0 is equal to f at negative, now I'm going to kind of skip ahead here, plus f at 0.1, or f at 0.1 minus f at negative 0.1. So this is the x plus h, this is the x minus h, x is 0, h is 0.1, over 2 times h. Do you see where I'm getting that from? And I'm just going to put an approximate here because we've got some error and stuff. You'll see the error difference. So that means I'm going to take 1.0517 minus, now I do need help. This minus that, please.
It's 0.20033.
That's great, thank you. And then that's divided by 0.2. Look, I mean, you can already see what's going to happen here. Can you do that for me then, please, sir?
Yeah, I got 1.001667.
Look at that. 2 extra places of precision. This is the order squared approximate. This is the h squared. This is the h. Look at the difference here. This thing minus the truth is within 0.1 of the truth. This thing here, minus the truth, is within 0.1 squared of the truth, 1/100th of the truth. It's even a little bit better than that. The smaller h goes, the more amazing this approximation would be. This stuff is so ripe for Excel. Like this, I was playing around with this when I heard the story about your sister, Kyle. It's just so much fun to do these derivatives this way. So I think I'm going to end it today because I don't want to get started, but let me leave you with a problem because I don't want to give you homework yet. I would like to leave you with something to work on in the meantime. And okay, so this is a weird one. I would like you to take this is what we'll start with on Wednesday. So take this series, which you already know, blah, blah, blah. Find this series. Notice there's 2h in there. All right. And then try to find an A and a B so that we can get an expression for f prime of x in terms of some multiple of this guy plus some multiple of the other 2h step version. So write those series out, and you're looking for multiples of one plus or minus multiples of the other that cancel out everything. So what I want is this. I want it to cancel out enough stuff that I end up with a good error term. Now, we can keep f at x. You're going to need that. We're going to need samples from at the point. But other than that, cancel out as much as you can and come up with a good expression. And then divide both sides by the power of h that you're about to find. So that's going to turn out to be some multiple of just h to the first power. So this will be a first order, order h approximation, but it's going to be really weird and really different. If you end up wanting to see how this is done, you could look in the book. It's
look at the chapter on derivatives and just maybe either think about that or read through it before Monday, and I'd be super appreciative. Thank you, friends. Dang blah. Did you already hit stop?
Scare me.
You did. Oh, did I scare you? I'm sorry. You did hit stop. Somebody hit stop.